Bismillahirrahmanirrahim. Welcome students to the online lecture of digital logic design. In the today's lecture, we will be continuing with the analysis part, and we will be discussing the analysis with the JK and the T flip-flops. In the last lecture, we started the analysis section with the D flip-flops, and now we will be continuing it with the JK and the T flip-flops. Because we will be discussing the JK flip-flops and the T flip-flops, so for the revision sake, we are saying this chart. We have already seen all these flip-flops and their equations. For the JK flip-flop, if we have both of them values J and K equal to 0, then we don't have any change in the output. While if we have K is equal to 1, then that would turn our flip-flop into the reset state, and if we have J equal to 1, it will be turning our flip-flop into set state, while if both of them are equal to 1, then the present state would be complemented. Similarly, for the T flip-flop, if we have 0 at the input or the T input, then we would not have any change at the next clock's output. While if we have T equal to 1, then whatever the value that is present at the output of the flip-flop will be complemented. Similarly, their expressions are represented in this form. So far we have discussed the analysis section of the sequential circuits using the D flip-flops. In the D flip-flops, the functionality of the overall circuits become quite simple because of the fact that for the D flip-flops, whatever the input is present before the clock edge, automatically is connected to the output after the clock edge. So there is no further thing involved in it. But as we have seen for the JK and the T flip-flops, they depend differently on the input. So for them, if we have to design a sequential circuit using the JK flip-flops and the T flip-flop, we have to modify our mechanism slightly so that we could adjust these changes in the system. Say if we have a system that is represented in a form of JK flip-flop, which is represented in the last slide as this one, you can clearly see that the system has two states, A and B. Both are representing the outputs of these flip-flop. This one is, you can say, the first flip-flop, and this is the second flip-flop. The inputs connected here are through some combinational gates. The main input here is the X, while it is connected through X in this form and J through this form. Similarly, our input to the next flip-flop, JK flip-flop, J and K, are represented through these combination circuit. For all these points, we can easily determine that what are the equations of the JK for each of the flip-flop, and we can represent in a form of like this. The input for the first flip-flop, which is represented as JA is equal to the B, while the KA is equal to B into X complement. Similarly, for the second flip-flop, we have the JK is JB is equal to the X complement, while the KB is equal to A complement X plus A into X complement, or the exclusive OR between the two terms. First, what we need to do is that we form the same kind of state transition table. But now when we form the state transition table, it would be a little bit different from the one that we have discussed for the D flip-flop. Because when we are calculating the next state, we would be requiring that what is the current states of the input system or input of the flip-flops. Because now the flip-flop inputs are separately represented here as just to help us in designing what would be the value of this state, say next state. So if we have to calculate the values of the next state, we can use two type of approaches. One is that we derive the equations for the inputs of these JKs and JBs. And the next second approach is that we derive the state equation for the next outputs of these one. Means we derive the equation of AT plus 1 and the BT plus 1. We can use both these approaches to solve this table. So first we discussed that how we can solve this using these terms. Mean we find the next state using the inputs of these flip-flops. Say if we have both A and B are equal to 0, and we have input that is also equal to 0, then what would happen is that we would get J A is equal to 0, so we would be getting 0 here. Similarly, Ka would be also equal to 0. Similarly, for the second flip-flop, what would happen is that JB is equal to the X complement, so it would become equal to 1, while KB is the exclusive OR of these two terms, so it would also equal to 0. So now what we have here is that we are having the values of JA KA and JB KB. Having JA and KA 0 would set the next state of A equal to 0, because the current state will hold and there would be no change according to the JK flip-flop table. So we would be having A equal to 0. But for the second flip-flop, when JB is equal to 1 and KB is equal to 0, then that would actually set the flip-flop, means that the output would be equal to 1. So in that case, B would be equal to 1. So in this manner, depending upon the values of the present states and the input value, we calculate the value of JA, JK, KA, JB and KB. And from these values, we calculate the next states. We first calculate the inputs of the flip-flops, and then from the input of these flip-flops, what we do is we calculate the next states of the system. There is an alternate method to this thing, that we can also solve this thing using the state equation. That instead of writing the input equation for the flip-flops, we write the output equation of the next state. Means we write the equations for the A t plus 1 and the B t plus 1. Now we would see that method. As we know, for the JK flip-flop, the output are represented as this one. Similarly, for the if the flip-flop is represented as JK flip-flop is represented as B, then its state equation is, or the next state equation is represented as this one. So what we do is we simply place the values that we have derived in the last slides into this part, because you remember we have the K equal to Bx complement, so we just put it here, and Ja was equal to B, so we just put it here. So in this way, what we are doing is that we put the input equations of the JK flip-flop to the main equations of the JK flip-flops, and we would be getting the equations for the next states, A t plus 1 and B t plus 1. We have just place the equations here. So in this way, we could also form the system or the state table, and from the same state table we can just then construct the state diagram of the system. And for constructing the state diagram of the system, as we know, because there are two flip-flops involved in this system, so we would be having total of 4 different combinations. Each combination will be representing a separate state. So for A, B to have a value of 0, 0, we would be actually representing the current state of the system, while the next state is represented as A 0, 1, while the next as 1, 0, and then we have the A 1, 1. So in this way, we would be representing the states, and the transition between them can be represented or expressed using the table which we have derived in the last slide. This one, we will be using this one to represent the state transition. For example, if we are at the present state is 0, 0 and the input is also 0, our next state would be equal to 0, 1. So if our current state is 0, 0 and our input is 0, we would be moving to this state. Again, there is no separate output in the system, so that's why we are not representing after anything after the /1. So in this way, we represent the state transition diagram. Similarly, once we are here, then we would see that what is the behavior of the system after the next clock cycle, and that will be dependent upon the input of the system. Say if the VR current state is at 0, 1 and our input is 0, x is the value of x is 0, then what would happen? We would be moving to the state 1, 1, and from the 1, 1, if we have the input equal to 1, then we would stay at 1, 1 till the input is 0. So if the input is not changed from 1 here, then we would remain here at the state 1, 1. We could also represent these state in a form of, say, a separate number or the binary equivalent subscript. Say this is represented as S0, this is as S1, this is as S2, and this is as S3. And if we are, say, at S3 and then the input 0 occurs, then what would happen is we would move to state 0, 0 again. Similarly, if we are having at state 0, 1 and the input 1 occurs, then what would happen is that we would move to state S2 or the 1, 0 state, and we would remain at this state till we have x is equal to 1. So in this way, the whole circuit diagram will represent the functionality of that system, that how our system behaves. If you see that from the state transition diagram, we only understand the basic working of the system, regardless of what kind of internal circuitry or the type of the flip-flops that are utilized in this circuit. Because this state diagram could also represent a system that is constructed of only the D flip-flops. And because it is more easier for any person who is not who don't have much understanding about the digital logic design, he can understand the working of the system more efficiently using this state diagram, other than if he has to understand the system functionality from these equations. Now we would see another type of flip-flop, which is known as the T flip-flop or the toggle flip-flop. In the toggle flip-flop, what happens is that if our input T is equal to 0, then our current state hold. It means that we don't have any change in the next state output. While if our current state input is equal to 1, T is equal to 1, then whatever is present at the output is complemented. The state transition equation or the characteristic equation is represented here as this. Suppose we have a system here that is represented in a form of two flip-flops. It has some combinational part for both the input and the output of the system. For this system, we would be analyzing that what's the main functionality of this system, or how this system is performing. We would having two states here. One would be A and other would be a B. So we would be overall there would be four state of the four circles representing the state diagram. But first we have to represent this whole process in a form of a state transition table. To represent it in the form of a state transition table, we first write the equations of the flip-flops. For the first flip-flop, we have equation is equal to Bx, while the second flip-flop, as we have seen in the last slide, is equal to the directly connected to the input X, while the output is the AND of the two flip-flops output A and B, so it is represented as A and B. Similarly, again we have the procedure that we could solve this system in form of two ways. One is that if we write the separate equations or a separate section which is representing the inputs equation of these two flip-flops, or we could write them in a form of the characteristic equation of the next state, or AT plus 1 and the BT plus 1. So if we now express this system in a form of the next state output of these flip-flop, what we do is we have these input equations of the flip-flops. We would put them in the main equation of the T flip-flop, which was the T exclusive OR of the Q, or the output of the flip-flop. And if we put these values here, we would be getting this equation for the output of the next output of the first flip-flop, and we would be getting this equation for the next output of the B flip-flop. From this one, we can easily construct this table, because we are having two states here and one input here. So we would have a total of 8 different entries in this table, and for each binary combination of these values, we would be calculating what is the next state or the next value that we would be moving. So the next state is calculated by simply putting these values in these two equations. If we put, say, for the first one, if we solve the first one, we have 0 0 and x is also equal to 0. So if we put all these values here, because all these terms are and this is the end, this is the end, and this is the end, so its result would be equal to 0. So a, we would have a equal to 0, while b is here, next term of b is represented as exclusive or of x with the b. So value of b here is 0 and x is also here equal to 0. So for the exclusive or of different inputs, we would be getting b equal to, the next value of b would be equal to 0. And similarly, if you calculate the output, because both of the current state a and b are equal to 0, so the output will be also be equal to 0. If you have to remember that for the output, we are concerned with the current state and not with the next state. Similarly, we can calculate all the patterns here for the next combinations. Say if we follow this combination, we have a equal to 1, b equal to 0. Then what would happen is that for a equal to 1 and b is equal to 0, if we simply put the values here, we would be having this term would be equal to 1. So it means that a is next value of a, or a t plus 1 is equal to 1. And for b, because b is equal to 0 and the input x is also equal to 0, we would have the next value of b as 0. In this case, because one value is 0, so we would be getting output also equal to 0. So we would have output equal to 0. Now we have to draw the state diagram of the system. Because the output here is not dependent upon any part of the input, that's why in the state diagram what we have done is that we are representing this output in a form of slash here. So because in the previous state diagrams we have seen that we were representing in this form of these arcs, that we were representing these input the output values, but because for this circuit you have seen that the output is dependent on the current state of the system. So we, when this happens, we represent the state transition or the state having this slash thing, that is representing the output of the system. And from this table we can easily plot this state diagram. Say if when we are in state 0 0 and the input is 0, what would happen? We would remain at that state. We would only move to the state 0 1 or the next state when we have input equal to 1. Similarly, we would remain at state 0 1 till we have x is equal to 0, and when we have an x is equal to 1, then we would move to the next state. Similarly, when we are at 1 0, what would happen is that we would remain at 1 0 if x is equal to 0, and if x is equal to 1, then we will be moving to the next state. So in this way, if you see that this is basically example of a binary counter. We are moving from 0 0 0 1 1 0 1 1 and again 0 0. So this is example of a binary counter. Whenever it gets an output input equal to 1, it moves to the or increments its value by 1. Whenever the input is 0, it remains at its current value. So this is example of a binary counter which is designed using the T flip-flops. Whenever we have input equal to 1, we would be moving to the next binary value. Say first is 0 0 first, and then if the input occurs 1, then we would move to 0 1, and if from that position 1 occurs, we would move to 1 0, and if 1 occurs, then we would move to 1 1, and similarly it would be reset after this state again to the 0 0. We have discussed a few different types of state diagrams here. These state diagrams follow two special structures which we represent as Mealy and the Moore models. The Mealy and the Moore models represents the type of the state diagram or the state machine that we are using. In the Mealy model, the outputs are the function of both the present state of the system and the input of the system. Say if the output changes, output would change if the input change during the clock pulse period, because the outputs are function of both the present state and the input. So in this type of circuits, we could have some synchronization issue, because the input is not synchronized, and whenever the input value is changed, it could affect the value of the output. While in the Moore model, what happens is that the output are functions only of the present states of the system. So these are the, as you can say, the outputs are synchronous with the clocks that are governing the process of these flip-flop. In the graphical forms, we can represent these two things as Mealy machine and the Moore machines in the form of these two diagrams. You can see that for the Mealy machine, the output is have some part of the input involved in it. From this signal, we can see that there is some part of input that is also involved in the output part, or you can say the combinational circuit or the gates that are connecting the outputs involve some part from the input. While in the Moore machine, the outputs are only connected to the current state of the flip-flops. They are not connected directly to the inputs. We would also see a few examples, because these are the few examples that we have discussed in the last two lectures, this one and the last one. This is the example of the Mealy machine that we discussed in the last lecture. This is Mealy because in this way you can see that the output, which is Y, is not only dependent upon A and B, but also on the value of this X, because X is connected here in the form of complemented form, while this is from the A and B, the outputs of the flip-flops. So because it is dependent upon the value of X, that's why it is called as the Mealy machine. And we have also discussed few examples for the Moore machine too. And the Moore machine, we don't have a separate connection of input with the output. For example, this first one, in this one we didn't have even a separate output Y. So when we don't have a separate output Y, the A and B are considered as the system output or the next state only. So in this case, you can see that A and B are just the separate outputs of the system. So there is no involvement of input in the output from A and B. So that's why we are saying that this is the Moore machine. And another example, we have also seen that for the T flip-flop circuit. In the T flip-flop circuit, we have just studied this example. And in this example, you can clearly see that the output Y is only dependent upon the current state of the two flip-flops. This is the first flip-flop A and this is second flip-flop B. So the current output is only dependent upon the current state of the flip-flop. So it is not dependent upon the input of the system. So its value will only be changed after the specific clock cycle. So it will be a synchronized one. So this is also an example of the Moore machine. Kindly do read these pages for better understanding. Thank you.